Dear students, in previous class we have discussed about Bessel's expression and a problem related to the Bessel function, right? Now, let us move to the orthogonality property of Bessel function. Now, what is the statement? The statement is like this: if alpha and beta are two distinct roots of Jnx equal to 0. Okay, suppose if you solve Jn of x equal to 0, we'll get there are two roots alpha and beta. Then prove that integration x jn alpha x into jn beta x dx limits from 0 to 1. That is x limit from 0 to 1, which is equal to 0 when alpha not equal to beta. And its value is half into jn dash of alpha whole square for alpha equal to beta. Okay. Once again here alpha beta are two different roots. Then integral limit x from 0 to 1 x jn of alpha x into jn of beta x dx, which is equal to either you will get 0 or half jn dash of alpha whole square. 0 for alpha not equal to beta, that is first root not equal to the second root. And if both roots are same, then we will get this result. Okay. Now let us move to the proof. See, we have already the formula of Bessel's expression. What is that? X square d square y by dx square plus x dy by dx plus x square minus n square into y equal to 0, right? Now here we are considering the solution of one more expression, that is Jn lambda x. Suppose Jn lambda x be the solution of the equation. This one, x square d square y by dx square plus x dy by dx plus lambda square x square minus n square into y equal to 0. Suppose u and v are two associated differential equation. What is that u? U equal to jn of alpha x. Instead of lambda, I am replacing alpha because there are two roots. One is alpha and another one is beta. And let v equal to jn of beta x. Then the associated differential equations are what? Instead of y, we are taking u and we are taking v. Instead of lambda x, we are taking alpha x and beta x. Now, suppose if you replace this concept in the given expression, what you will get? X square. Instead of y double dash, you will get u double dash plus x u dash plus here alpha square x square minus n square into u equal to 0, right? Just instead of y, we are replacing u for the first equation. What about second one? X square v double dash plus x v dash plus beta square x square minus n square into v equal to 0. Call it as equation 1 and equation 2. Now, let us multiply equation. Suppose if you multiply equation 1 by v by x and equation 2 by u by x, then what you will get? Multiply here v by x. So, x square u double dash into v by x. So, x get cancelled. Remaining term x u double dash into v. Plus, here x u dash v by x. Again x get cancelled. U dash v. Plus, what remains here? See here, alpha square x square uv by x. So, what happens? 1x get cancelled. What remains? Alpha square 1x remains uv. Right? Alpha square uvx. Then minus n square uv by x equal to 0. Call it as equation 3. Similarly, multiply equation 2 by what? U by x. So, what you will get? X v double dash u plus here u v dash plus beta square x u, right, minus n square u v by x, right, equal to 0. That is equation 4, right. See, x u v double dash plus uv dash plus beta square uvx minus n square uv by x equal to 0. Now, can we cancel this term by subtracting See here minus n square uv by x. Again same we will get here in the next. So equation 3 minus equation 4. So what you will get? Equation 3 first expression is what? X u double dash v, right? First expression. For the equation 4, x u v double dash. So what we will get? X u double dash v minus x u v double dash. Then u dash v minus uv dash, right? Plus alpha square uvx minus alpha square uvx. Then minus n square uv by x plus n square uv by x. So this last term vanishes, equal to 0. What is common in this? X is common. Can we keep out? X outside. U double dash v minus v double dash u plus u dash v minus uv dash plus what is common here? uvx common, alpha square minus beta square, right? Equal to 0. Now here just to concentrate on the first two terms, equal to remaining you keep into the RHS. Then what you will get? See here, it is just like a product rule, right? First function derivative second plus second function into derivative first. See here, if you take d by dx of x into vu dash minus uv dash, check whether it matches to this first two terms or not. See here, first term as it is. Now differentiation of this, what you will get? vu double dash plus u dash v dash minus u dash v dash. So u dash v dash get cancelled. Then again minus u v double dash. See, we are getting this first term plus second term as it is, that is vu dash minus uv dash into derivative of x with respect to x is 1. Now which is equal to what? Take this to the RHS. So minus alpha square minus beta square into uvx. Now to eliminate this negative sign, can we interchange the term inside this? So that what you will get? D by dx of into x of vu dash minus uv dash equal to beta square minus alpha square into uvx. Okay. Now let us integrate this with respect to x on both sides between the limits 0 to 1, because they have given 0 to 1. See here, we need to integrate this, right? Now integrate the given expression with respect to x on both sides between limits what? 0 to 1. Then what we will get? Integral limit 0 to 1 d by dx of x into vu dash minus uv dash dx equal to, here alpha square minus beta square or beta square minus alpha square, this is the term constant, right? Take it outside the integral sign. What remains? Integral limit 0 to 1 uvx into dx. Now simplify here. We now one expression, different integration of differentiation of function means only function remains, right? Because differentiation and integration are reversible process. So here what happens? Only the term containing function remains. So what happens here? X into vu dash minus uv dash, where x varies from 0 to 1, equal to what? Beta square minus alpha square, integral limit 0 to 1 uvx dx. Now apply upper limit, then lower limit. Wherever x, apply upper limit here 1. So what will get? 1 into vu dash minus uv dash minus 0 into any quantity, that is 0, equal to beta square minus alpha square, limits from 0 to 1 uvx dx, right? Call it as equation 5. But actually what is u and v we have chosen in the beginning? We have chosen u equal to jn alpha x and v equal to jn beta x. Now I want here u dash and v dash term. So just find the derivative of u and the derivative of v. So what is u dash? Derivative of jn alpha x is Jn dash alpha x into coefficient of x is what? Alpha, right? Similarly, what is derivative of v? That is v dash, which is equal to what? Jn dash of beta x into beta. So we are familiar with the u dash, v dash. Just replace all these expression in the equation 5. So expression 5 becomes what now? V is nothing but Jn beta x, right? U dash nothing but alpha into Jn dash alpha x, right? Minus, now what is U? Jn alpha x. What is V dash? Beta Jn dash beta x. Now which is equal to beta square minus alpha square. Now integral limit 0 to 1. What is U? U is Jn alpha x. What is V? Jn beta x. Then into x. See here, into x dx. Now how will you simplify this expression? See. Now can we write it simplified form? That is alpha jn beta x jn dash alpha x minus beta jn alpha x jn dash beta x equal to beta square minus alpha square integral limit 0 to 1 x jn alpha x into jn beta x dx. No need to touch with the RHS, you have to write same. Now I want what? Integral limit 0 to 1. We need the expression of integral. So what is this expression? That is integral limit 0 to 1 x j n alpha x into j n beta x dx, which is equal to what? This term will come to the LHS, then it will come in the denominator part, right? So 1 by beta square minus alpha square into what? Alpha jn beta x jn dash of alpha x minus beta jn alpha x into jn dash of beta x. Call it as expression 6, because now we need to check when alpha equal to beta and when alpha not equal to beta, then what we will get. Now since alpha and beta are distinct roots of jn x equal to 0. Now, what is meant by root? Root of the expression, root of the given equation means what? The value which satisfies the equation. That means if you put that value, you should get answer 0. Then only we can say that the given value satisfies the equation, that is the root. So here alpha and beta we have mentioned, it is the root of the equation jn x equal to 0. What is meaning of this? That is jn alpha equal to 0 as well as jn beta also equal to 0. With this result, RHS of 6 becomes what? 0, provided beta square minus alpha square not equal to 0, and if it is not equal to 0 means beta also not equal to alpha. So what happens here? Since jn beta 0, even jn alpha 0, that is nothing but 0 here 0. But beta square minus alpha denominator should not be 0. If it is 0, then you will get infinity term, indefined, not defined. So here what happens? This is the case when beta square minus alpha square not equal to 0 or beta not equal to alpha, right? Therefore, integral limit x, here limit 0 to 1, x jn of alpha x into jn of beta x dx equal to what? 0 for alpha not equal to beta. Now what about the next case? Now let us discuss one more case, that is we shall discuss the case for alpha equal to beta. If alpha equal to beta, then the RHS of equation 6 becomes what? Indeterminate form, right? Already we have discussed. See here. Suppose alpha equal to beta here. Then what happens? See, jn alpha x, jn dash alpha x. Here alpha, jn alpha x, jn dash alpha x. So same term 0. Again alpha equal to beta means alpha square minus alpha square, again 0. So it will be in the form of 0 by 0 form, that is indeterminate form, right? Therefore we shall evaluate this by equating the limits on both sides as beta tends to alpha and keeping alpha fixed. Once again, if alpha equal to beta, then the RHS of the given expression becomes what? It will convert to the indeterminate form, that is 0 by 0. Now, in this case, we have to evaluate the given here this by equating the limits on both sides as beta tends to alpha, right? Keeping alpha fixed. So what you will get that time? Just apply the limit beta tends to alpha here. See, limit beta tends to alpha, integral limit 0 to 1, x j n alpha x j n beta x dx. Again here you have to apply limit beta tends to alpha, and this is the same. Okay, see. Now, since alpha is fixed, so that means what? We have taken alpha is the root. Now, therefore, Jn alpha equal to 0, as alpha is a root of Jn x equal to 0, right? Therefore, here what happens? X Jn alpha x, Jn beta x dx limits from 0 to 1, which is nothing but what? Limit beta tends to alpha 1 by beta square minus alpha square. Now, alpha Jn beta into Jn dash alpha, but Jn alpha equal to 0. So what happened here? Jn alpha equal to 0 we have taken already. So the second part vanishes. Still what we are getting here? Still we are getting what? 0 by 0 form. If you apply beta tends to alpha, what happened here? Again, it is in the form of 0 by 0 form. So what we have to do if it is the expression of 0 by 0 form, then we have to apply the L'Hospital's rule. Here you have to make one small correction, that is here you are applying beta tends to alpha, right? So that time this is alpha x. So Jn alpha x into Jn alpha x. Okay, here this concept here missing. Limits from 0 to 1 x Jn alpha x into Jn alpha x. So Jn alpha x into Jn alpha x is nothing but Jn alpha x whole square. So that only we have explained here. Dx equal to limit beta tends to alpha. Here what happens? Just apply the L'Hospital's rule. That is what we have to differentiate with respect to what? We have to differentiate here. So what you will get? Jn dash beta into Jn dash alpha. Now with respect to beta we have to differentiate, right? And apply the limit as beta tends to alpha. See here, alpha keep as it is constant, Jn alpha dash also you keep constant. Differentiate this Jn dash beta, and here differentiation is 2 beta. Now apply the limits for beta as alpha. Then what happened here? See, Jn dash beta, Jn dash alpha here. Now, since here 2 beta, now we are applying the limit beta as alpha. So both alpha alpha get cancelled. Even this also changes to alpha. So Jn dash alpha into Jn dash alpha, that is Jn dash alpha whole square divided by 2. So this is only the proof for the second one, alpha equal to beta. That is, see here. Further, we have the recurrence relation, that is Jn dash x equal to n by x, Jn x minus Jn plus 1x. Here, this concept either you can apply or you can leave at the previous stage also. No issue. This one no need to stress more. Now here, instead of x, just put alpha. So Jn dash alpha equal to n by alpha Jn alpha minus Jn plus 1 into alpha. But what is Jn alpha? Already we have taken 0. So Jn dash alpha equal to what? Minus Jn plus 1 alpha. So because of this, what we will get? Jn dash alpha whole square is nothing but Jn plus 1 dash plus 1 alpha whole square. So this becomes what? The given limit, integral limit 0 to 1 x Jn alpha x whole square dx equal to 1 by 2 Jn plus 1 dash of alpha whole square for alpha equal to beta. So this result is known as Lomel integral formula. But up to here it is very very important. You need to remember up to here compulsorily. Okay. Now once again we will revise the concept. orthogonality property, it is very important. See, orthogonality relation of Bessel function. If alpha and beta are two distinct root of j n x equal to 0, then prove that integral limit 0 to 1 x j n alpha x into j n beta x dx, which is equal to 0 for alpha not equal to beta, and half j n dash of alpha whole square for alpha equal to beta. Okay, now first we have to consider the standard equation. Let Jn lambda x be the solution of the equation x square d square y by dx square plus x dy by dx plus lambda square x square minus n square into y equal to 0. Now instead of alpha we have to choose, instead of lambda we have to choose alpha, and instead of lambda we have to choose beta. Now what you will get here, if u equal to, instead of y, you have to choose. If u equal to jn alpha x, similarly v equal to jn beta x, then the associated differential equations are what? X square u double dash plus x u dash plus alpha square x square minus n square into u equal to 0. Similarly, x square v double dash plus x v dash plus beta square x square minus n square into v equal to 0. Now multiply, call it as equation 1 and 2. Multiply equation 1 by, here there is missing term is v, so v by x, and here u by x. Now multiply equation 1 by v by x and equation 2 by u by x. Then this expression becomes x u double dash v plus v u dash plus alpha square u v x minus n square u v by x equal to 0. Call it as equation 3. Similarly, if you multiply equation 2 by v, here u by x, and simplify, you will get x u v double dash plus u v dash plus beta square u v x minus n square u v by x equal to 0. Call it as equation 4. Now subtract equation 3 minus equation 4. You will get x u double dash v minus x u v double dash plus v u dash minus u v dash plus alpha square u v x minus beta square u v x, and this term get vanished equal to 0. Now what is common in this first two term? X common, keep it out. V u double dash minus u v double dash plus v u dash minus u v dash plus, here u v x is common, alpha square minus beta square equal to 0. Or this two expression together can be written in the form of d by dx of x into v u dash minus u v dash. This is just like a product rule. Derivative of u v is nothing but u into v dash plus v into u dash. Same thing here. If you simplify, you will get this expression only. Now keep this thing in the RHS, 0 minus of this quantity. So what you will get? Minus u v x into alpha square minus beta square, right? Or you can avoid this negative sign by interchanging these two elements. So what? D by dx x into u v u dash minus u v dash equal to what? Beta square minus alpha square into u v x. Now integrate this relation both sides with respect to x from 0 to 1. So what you will get? Integral limit 0 to 1 d by dx of x into v u dash minus u v dash dx equal to beta square minus alpha square, limits from 0 to 1 u v x dx, right? Now let us continue with this. See, that is, if you integrate with respect to x from 0 to 1, you will get x into v u dash minus u v dash, limits from 0 to 1, because derivative of integration cancel each other. Only remaining term is what? Only the function with the limits 0 to 1. Equal to what? Beta square minus alpha square, integration limits from 0 to 1 u v x dx, right? Now apply upper limit then minus lower limit. So you will get v u dash minus u v dash minus 0 equal to beta square minus alpha square, integral limit what? 0 to 1 u v x dx. Call it as expression 5. Now, since we have already discussed u equal to jn of alpha x and v equal to jn of beta x. So, what is u dash? Derivative of this jn of alpha x, derivative of this is jn dash of alpha x into alpha. And what about this v dash? that is Jn dash of beta x into beta. Now substitute it back in equation 5. So Vu dash, what you will get here? Jn beta x into Jn dash alpha x into alpha minus Jn alpha x into Jn dash beta x into beta equal to what? Beta square minus alpha square, limits from 0 to 1. Here x as it is, u is nothing but Jn of alpha x, v is nothing but Jn of beta x into dx, right? Now simplify, you will get alpha Jn beta x into Jn dash of alpha x minus beta Jn alpha x into Jn dash of beta x equal to what? Beta square minus alpha square integral x Jn alpha x into Jn beta x dx, limits from 0 to 1. But we require only this integral part. For this we have to keep this constant term to the another side. Then what we will get here? Integral limit 0 to 1 x Jn alpha x into Jn beta x dx, which is nothing but 1 by beta square minus alpha square into what? Alpha Jn beta x into Jn dash of alpha x minus beta Jn alpha x into Jn dash of beta x. Now here alpha and beta are distinct root of the equation, right? So Jn x equal to 0, this is the standard equation. If you put alpha and beta both are what are roots, they are satisfying the equation, means Jn alpha equal to 0 as well as Jn beta equal to 0. Now if this is the case, then what happens? Jn alpha 0, Jn beta 0 means the total RHS part will become 0, right? Because here Jn beta x, here x we are applying upper limit 1, then it will be Jn beta, and here it will be Jn alpha. So if alpha and beta satisfies the equation, or alpha and beta are the roots of the equation, which is nothing but Jn alpha 0 and Jn beta 0, so the RHS part completely vanishes. But the thing is, you should keep it in one thing in mind, that is beta square minus alpha square, it should not be 0. Because if you choose this equal to 0 and here also 0, 0 by 0 indeterminate form, so we cannot simplify as it is. So first you have to substitute one condition where this beta square minus alpha square, which is not equal to 0, that is the condition. Okay, then the given expression becomes what? Therefore x Jn alpha x into Jn beta x dx, limits from 0 to 1, which is equal to 0 for alpha not equal to beta. Okay, because here alpha not equal to beta, beta square minus alpha square not equal to 0, that's it. Now let us continue with the second case. Suppose alpha equal to beta, then what happens? If alpha equal to beta, obviously the expression 6, numerator also 0, denominator also 0, that is the indeterminate form. Therefore we shall evaluate this by equating the limits on both sides as beta tends to alpha and keeping alpha as fixed. One thing you have to keep fixed and rest you have to leave. Now that is limit beta tends to alpha, integral limit 0 to 1 x Jn alpha x into Jn beta x dx, which is nothing but what? Apply the limit as beta tends to alpha, 1 by beta square minus alpha square into alpha Jn of beta into Jn dash of alpha, right? Minus beta Jn alpha into Jn dash of beta, because you are applying upper limit x is 1 and lower limit x is 0. So lower limit vanishes automatically. Now what we have given here, since alpha is fixed, we have chosen only alpha fixed. That means alpha satisfies the root, or Jn alpha equal to 0. Then what happens? This becomes what now? Integral limit 0 to 1. This is nothing but x Jn alpha x into Jn alpha x. It should be alpha. By mistake here beta we have mentioned alpha dx. Now which is equal to what? Limit beta tends to alpha, 1 by beta square minus alpha square, alpha into Jn beta into Jn dash alpha. And what is Jn alpha? Jn alpha is 0, we have mentioned already, because it is the root and we have kept it as a fixed value. So this part completely 0. Again here what happens? Again if you apply the limit beta as alpha, again 0 by 0 form. So what we will get? Indeterminate form. So for that what we have to do? Apply L'Hospital's rule, or we can call it as L'Hopital's rule. So what we will get? Differentiate numerator and denominator separately with respect to the constant here. So what you will get here? 0 to 1 xj and alpha x whole square dx, which is equal to what? Limit beta tends to alpha. Here to beta it should be, after applying beta limit as alpha, it will become alpha. Okay. So alpha j n dash beta into j n dash alpha divided by 2 beta. So here, but beta is what? In terms of alpha we are applying. Here also we are applying in terms of alpha. So wherever beta we have to apply alpha, because limit as beta tends to alpha. So what? Alpha alpha get cancelled, j n dash of alpha into j n dash of alpha divided by 2. So j n dash alpha whole square divided by 2. So this integral limit is 0 to 1 x j n alpha x whole square dx, which is nothing but j n dash of alpha whole square divided by 2. This is the case for alpha equal to beta, right? So we need to prove this result for orthogonality condition. Okay.